All right, we're back. We're on page 35 of math analysis. And so we're talking about trig stuff, and we've been doing a lot with the unit circle. And so let's see what this has to do with that. So circular definitions of trig functions. We have unit circle definitions of the trig functions. We said that on the unit circle, every ordered pair, xy, becomes cosine of theta, sine of theta. And so that means that x is cosine of theta and y is sine of theta. You'll find as you do enough math, x frequently, if not always, goes with cosine, y frequently, if not always, goes with sine. Like it's a very close relationship that they have. So there's a reason that these worked out really well. And the reason that they worked out so well is that when we drew our triangle on the unit circle, or using the unit circle, or kind of like inscribed within the unit circle. It's not really inscribed because it only has like one of its vertices, but whatever. I don't know that we need the right word there. So get on there. That's definitely not right, but it's close. So when we did this, because it's a unit circle, the radius is 1, which made the hypotenuse 1. So when we tried to do opposite over hypotenuse, we got y over 1. And when we did cosine, did adjacent over hypotenuse, we just got x over 1. So it's really the fact that the radius equals 1. Therefore, the hypotenuse of each of our right triangle definitions equaled 1. So what we want to deal with is we want to deal with like what happens if it's not 1, right? So an idea that we can use is basically similar triangles. So if you look at these triangles, these are going to be similar because they share this angle and they both have right angles, which means that triangles, what should we name these? ODB. So triangle ODB is similar to triangle, OCA. O is for the origin. You pretty much always do that. Okay, these are similar, and I'm going to say by angle. So angle. Two angles of a triangle of two. If two angles of two triangles are congruent, then the triangles must be similar to each other. So these are similar by angle. So if you look at it, you can see that that means that. So you can either, when I used to teach geometry, what I used to do is just use actually just use this. So like these are going to be in proportion. These are going to be in proportion, and what else? How do I get the other one? Like those are going to be in proportion. So like you look at it and you're like, all right, so the hypotenuse is like OA and OB. Okay, so if I do like OD divided by OB, that's definitely going to be the same as OC divided by OA, like guaranteed, right? Similar triangles. So what if, now in each of these, both of these actually equal OD and then OC, OA, OB. Both of these actually equal cosine. So these equal cosine of theta. So they have to be equal because they're in proportion because of the similar triangles, and it turns out they both equal cosine. So I guess I should do the sine one. So AC or CA, however you want to say it. So let's go with CA. So BD over OB is equal to, so BD and then AC over OA, and then both of those equal sine of theta. Now what's interesting about this, kind of, is that this is just how trig works, right? Like similar triangles, that's why they're ratios in simplest form usually. So what we could do is we could say that we have just like some generic point, and we'll just say that it's the point xy. And what we'll do is we'll treat that as if it's on a circle of radius r, and we don't really know what r is, but we kind of do. Can I do this? Are you going to become a circle? Nope. I want it to be a circle so that I can then like trace the part that I need. Holy cow, what is that? All right, one more. You know you want to be a circle. It doesn't want to be a circle. Okay, so you do your best, right? That's 100% wrong. Although maybe these aren't scaled equally. I don't know. So this is a circle with a radius of r. All right, so xy is a point on the circle centered at the origin of radius r. So if that's the case, then you know that x squared plus y squared equals r squared, or more specifically, you know that r is the square root of x squared plus y squared, which is a big deal. You're going to use that idea so many applications. We call it r for radius, even when it's not obviously a radius. It's like distance, really, in xy, we pretty much call r. So let's say that we have here, right? This is y, and then this, let me fill it in here, is going to be x. I'd rather use black for that. So I'll highlight it in a different color, but I'm going to call that x. So here you can see that since this distance, I'm going to actually highlight this. This is r. So just using that triangle, we can see that the cosine of theta is not just x, because it's not a point on the unit circle, but it is a point on a circle with a hypotenuse or a radius of r, so it's actually x over r. And we can also say that sine of theta is y over r. I feel like these notes are kind of all over the place. Like I've never loved these notes because I just don't really know why. But so say we had this. Okay, auto shapes are killing me here. It's like, why do I have to be so? There we go. And then let's have another one. So here, nope. It was good, and then I messed it up because I moved it. There. Okay. So if this part right here is 1, and then this part right here it like wants, okay, and this is r, and then this part would be sine of theta, and this would be cosine of theta. So I'm like building my similar triangles just to hammer home how this works. This would be x, and this, so this is if you want to like exactly follow what the notes are telling you to do. Y, right? So you can see by similar triangles that like, I don't know, like y over x is going to be sine over cosine. Y over r is going to be sine over 1, so sine is y over r. X over r is going to be cosine over 1, so yeah, so cosine is x over r. Like that's, if you want to use similar triangles, that's what you do. So how do we use this? Well, the way we use it is to solve problems like this. I call these point in the plane problems. You're given a point in the plane, you want to find all 6 trig functions, and you want to find the exact value of the angle. You want to find those things. So basically 7 things. Let's see if we can do this. So we're going to start off. Now you don't need to draw a triangle. I'm going to draw a triangle anyway. So here, I need a set of axes. And it doesn't need to be super accurate, like, or even kind of accurate, really. It's just got to be in the right quadrant so that you have the correct frame of mind. So what we're doing, remember the bow tie or the butterfly, whatever you want to call it. The triangle that we're going to draw, we got to drop our angle down here. And so this point is going to be the point -7, 24. Well, I know that 7, 24, 25 is a Pythagorean triple, so I know that this will be 25. But if I didn't know that, I would say that r is equal to the square root of -7 squared plus 24 squared, which I know is 25. But really, you should just know that 7, 24, 25 is a triple, and that's a 5. All right, so based on the definitions that we have so far, we know that we're going to find sine, cosine, tangent, and then we'll find 1, 2, okay, and then we'll find cosecant. So we don't really find these, we just take reciprocals. If you're doing anything else, you're out of your mind. Cotan. All right, so focus up on what we need, right? So we need sine should be y over r, so it should be 24 over 25. Now this makes sense to me because we're in the second quadrant and sine is positive, and I got a positive, so that feels good. Cosine should be x over r, so -7 over 25. Also feels right. We're in the second quadrant, cosine's negative, makes sense. Tangent's just sine over cosine or y over x. That doesn't change based on this definition. So we're just going to get -24 over 7, and then we take reciprocals. So you don't think about these definitions really, you just kind of go with your reciprocals. So that's totally fine, and we're done. We didn't get the exact value yet, but what I want to show you is another way of sort of thinking about this, which is the way that I've always done these problems. So what I do is I'm aware of what angle I'm supposed to be dealing with, right? The angle that I'm supposed to be dealing with is this. This is theta, right? What I'm going to do, though, is I'm going to focus in on a different angle and call it alpha. Actually, let me do this in a different color because this is some sketchy work. So that's going to be alpha. Now, alpha lives in a triangle that has a right angle and has the following sides. This distance, but I'm going to say it's a directed distance, is -7. And then this distance, which is also a directed distance, but it happens to be positive, so it's like not as big a deal, is 24. So if you look at this triangle and somebody says, in this triangle, what is the sine of alpha? So the sine of alpha would be 24 over 25, which if you look and see the sine of theta that we got is exactly the same. If I look at cosine of alpha, it's going to be adjacent, which is -7. It's a directed distance over 25, which is exactly what we got. Tangent is going to be opposite over adjacent, so it's going to be -24 over 7, and you can go from there. This is totally how I've always done these problems. I look at these, they're like reference triangles, but they're reference triangles that have negative sides if they need them. And it's totally fine. You'll get all the ratios correct. It's definitely a valid way of doing it, in my opinion, but you might not like it quite so much. And if you don't like it quite so much, don't use it. So let's find the exact value of the angle. So the angle, so theta is a quadrant 2 angle. We know that. So theta is an element of quadrant 2. So think about your formulas. If you know the reference angle, how do you find the angle? So I'm going to say, therefore, theta is equal to, I'm going to do this in radians, pi minus the reference angle. Now the question becomes, what is the reference angle? So the reference angle, the safest way to find a reference angle. So let's do this. So the safest reference angle. Well, which one do you know the most about going into the problem, right? So given a point xy, sine is going to be y over r. We're not given r, so we don't necessarily know that. Cosine is x over r. We don't know r. That's not safe. Tangent is y over x. We actually know x and y, so we know everything for tangent. So we're going to use tangent to find our reference angle, but we have to be careful. I'm going to say that it is the inverse tangent of the absolute value of y over x. So I think I'm going to do both absolute values and then switch back, and then probably not be really happy because that's not a very vertical line. We're going to use the absolute value. Why is the absolute value there? So absolute value to give quadrant 1 angle. So this is a very complicated issue. When you do an inverse trig function of a positive thing, you always get quadrant 1. You do inverse tangent of a negative, you get a very surprising result. You can try it on your calculator. You get a negative angle. But not only do you get a negative angle, you get a negative 4th quadrant angle. And it's just weird. Like, why is that happening? We're going to talk a lot about why that's happening. But our preferred reference angle all year long, and for the rest of math, is going to be inverse tangent of the absolute value of y over x. So that's our reference angle. So here, we can say theta is going to be pi minus the inverse tangent of the absolute value, so you don't have to write that by hand, of 24 over 7. Now, really briefly, I just want to show you something you can do on your calculator here. So you don't necessarily need to do this unless you're not like positive of your answers. That's some calculus stuff for later in life. So I'm going to say that t for theta, I guess, is pi minus arctan of 24 over 7. Okay, that's stored. Now what I'm going to do is the sine of t. And I get what I want, cosine of t. Exactly. Tangent of t. Excellent. So that's how you can check these, and you should. So after you find all your ratios, find the exact value of the angle, try to store that, and then ask your calculator, are you right? And it'll tell you if you're right. And that's kind of an amazing thing to be able to do. So I encourage you to try that. And I'm going to go back to the notes, and then I will stop this video here and then come back in another video and do more. So I think we're making pretty good progress on these notes. So I will see you in the next one. So hope you're finding these helpful.